So today we're going to look at lesson 7-3, and we're going to really look into what are logarithms, what is the graph of a logarithm, how is it related to an exponential function, which we spent a lot of time on this week, and we're going to graph those and look at some word problems. So let's get some vocabulary out of the way. And basically, we've got the logarithm that has some base of b. And so this is how a log function is typically written. Log of some base is equal to a log of some base of a number is equal to another number. Now, logarithms are actually the inverse of the exponential functions that we've been studying. So I'm going to teach you how to convert this to its exponential form. But the actual graph of a log is the inverse of the exponential functions. And so we'll talk about we'll review what inverses are to each other as well. And so if and only if, and so let's go back to our inverse function that we were looking at, or our exponential function that we're looking at. So x is equal to b to the y. So remember when we were actually looking at exponential functions, we said it was y is equal to b to the x. So notice that the x and the y are reversed here. This is the exponential function of this log right here. But you'll notice that in the exponential form of this log that the x and the y are reversed from what we've been studying because these are inverses of each other. And so I will teach you how to convert from this form to this form. And then you can read this as the log base b of x. In other words, the logarithm y is the exponent. So let's put that there. To which b, which is your base, must be raised to get x. So again, a logarithm equals y, which is your exponent, so y, which is your exponent, to which the base must be raised to get to x. So before we go any further, let me just give you an example. Would you or would you not agree that, well, let me go ahead and give you this first. So log base 10 of 100 is equal to 2. How would you write this in its exponential form, given the three numbers 10, 100, and 2? Don't you think about that? How would you write these three numbers in exponential form so that they make a true statement? I'm going to give you just a couple seconds. Think about that. All right, so 10, 100, and 2. Would you or would you not agree that if I took 10 and squared it, we would get 100? That's a true statement, right? So notice that for both of these, this is the log form, this is its exponential form. They are two different forms to identify the same thing. Notice that they both have the same base, but this 100 and this 2 are switched. So all we did was switch these. We took 10, raised it to the second power, and that equals 100. So essentially from a logarithm, what you get out of it is the exponent of the exponential form. So here's your exponential form. Notice that 2 is the exponent, and that's the answer to your log function. And so that's really what the log is, and that's what this is trying to tell you here. So y is the exponent. This value here, y, the answer to your log function, is the exponent that it would have in its exponential form. And so we're going to spend quite a bit of time going from log form to exponential form and vice versa, and then the rest of our time will be spent graphing. So let's go ahead and finish out our vocabulary. A logarithmic function is the inverse of an exponential function. A logarithm that uses base 10 is known as the common log. You can write log base 10 of y, some number, as just, so you can actually drop that logarithm or that base 10 and just write it as log of y. So essentially, if you don't see a base here, it's understood that it's got a base of 10. Normally, we would not write this log, which has a base of 10, with a 10 here. We would have just written a log of 100. And that's the only base that you can write that way. Our logarithmic scale is any scale that uses the log of a quantity instead of the quantity itself. All right, so let's look at characteristics of a logarithmic function. So your parent function, as we've been emphasizing all along, is going to be y equals log base b, and notice that your base is a subscript, so make sure it's not in the same line as your log of x. X is going to be some number. So notice that the log and the x are in the same line together. This is a subscript. Now it's important to note something about the base and this number here, whatever it is. It is vitally important that you realize and remember that b must be greater than 0. So it has to be positive, and b cannot equal 1. So it has to be greater than 0, but it cannot equal 1. In addition to that, your x also has to be greater than 0. So both this value has to be positive and this value must be positive. Neither one of these can be negative. And that's going to be something that explains why the graph of a logarithmic function is what it is. And then on top of that, the b cannot be 1. All right, so same thing that has occurred before. If this is our parent function, a stretch is going to be if we had some coefficient in front of the function right here called a. So you would have a stretch if the absolute value, because remember if a is negative, it's a reflection, is greater than 1, that's going to create a stretch. If we have a shrink, the absolute value of a will be less than 1, but greater than 0. And of course your translations come from h and k again. H is going to occur within the function to the x, and k is going to occur outside the function. And so they're going to look like y equals log some base b of, now I'm going to put the x in parentheses, so x minus h, and then plus k. So again, if you're adding or subtracting something to this x value, it's going to create a right-left shift, and it's going to be the opposite of what you think it would be. So if we have x minus 2, it's not going to shift left, it's going to shift right 2. But if we have x plus 2, it's not going to shift right 2, it's going to shift left 2. But remember, this is outside the function, and so it's exactly what you think it would be. So if we have a plus 2 on the outside, we're going to move up 2. A minus 2 on the outside means you're going to move down 2. So outside the function is an up-down movement, inside the function is a right-left movement. And so if I put all of these together, it's going to look like y equals, your stretch or shrink would come in front of this log, some base of x minus h plus k. And now we're ready to do some work. So I am going to stretch this out a little bit, but first we're going to look at this definition right here. So this is how you go from exponential form to log form, from log form to exponential form. So let's just see what the difference is between these two and what the similarities are. So notice that this is your exponent with a base and an exponent, and then it gives you some number. Over here, this kind of looks like a base and an exponent, but it's not really, and you have some number. Notice that both of these have the same number that we're using for a base, this b. So the base in our log and the base in our exponential function always remains the same. What changes is, notice that the x, which is our answer, switches to our what looks like an exponent here, or vice versa. So you notice that these switch. So this b to the x, if you will, becomes b to the y equals x over here. So these are just switching here and switching here. That's all you're doing. It's just a switch. So for instance, wouldn't you agree that 6 squared is equal to 36? So we're going to find its log form. And so all we have to do is take log. We're going to keep the same base. So the base here is 6, so we're going to keep the same base here as a 6. So these bases are the same. What's going to happen is these two numbers are going to switch. Instead of having a 2 here, so it looks like 6 squared, we're going to switch these two and we're going to put the 36 here. And so the 36 is going to go here, and the 2 is going to go over here, and there should be an equal sign in between. So I'm going to actually switch this around so that the bases are on the same side of the equal sign. So the base here is on the left side. I'm going to put the base here on the left side just so you can really see how that switch occurred. So 6 squared, that's a 2, equals 36. So one more time. Notice that our bases stayed the same, so those didn't change. But notice that the 2 and the 36 switch places. 36 here and the 2 here. So these switched, and I put the 36 here and the 2 here. So you try that with this one. What's your base? That's going to go here with your log. And again, I would switch these around. I would switch this so it would read, whoops, why do I do that all the time? So I would switch these around so it reads 3 to the 0 equals 1. You'll agree that that's a true statement. So you go ahead and write your log form. Pause the video, write your log form, restart the video. All right, so you should have log base 3, because there's our bases are the same, and then these are going to switch. So I'm going to put the 1 here and the 0 here. So then my 1 goes here, and my 0 is here, and my equal sign is here. And so there is my log form. Log base b of, or log base 3 of 1 is equal to 0. So then here, just because you have a bunch of fractions doesn't mean anything's changed. So again, I'm going to switch this so that I have 2/3 to the third is equal to 8 over 27. Again, I'm sure you'll agree that these are equivalent statements. We're just going to put this exponential form into its log form. So if you feel brave, you're not afraid of the fractions, pause the video, you try to convert it, and then restart the video. Okay, so you have log. Our base is right here because that's the base of the exponent, the exponential form, the base and the exponent. So my base here is going to be 2/3. Make sure you make that a subscript. And then all I'm going to do is switch the 3 and the 8/27 around. So the 8/27 goes here, and the 3 is going to go on the other side of the equal sign. And that's it. Congratulations. All right, so in this particular section, we are going to find the value of each log without using our calculator. And so in order to do this, we're going to try to attempt to get common bases on both sides of the equal sign by converting our log into its exponential form. And so we're going to try to do something that looks like this. We're going to create an exponent on one side that has a base of, some base raised to an exponent. And we're going to set that equal to something on the other side that has the exact same base, but maybe raised to a different number. So if I have two bases that are the same and raised to different looking exponents, the theory would be that the exponents should be equal to each other. So if I can get the bases to be the same, I can ignore the bases and just set their exponents equal to each other. For instance, let's look at A. So I'm going to make this really big. So as I look at A, I want to find the value of the log base 5 of 125. So in order to do this, I always like to take these types of problems and set them equal to x. So there's a couple ways I'm going to show you how to do this. So we'll do way one first, and then I'll show you the other way second. Now we'll just do it this way. I'm not going to confuse you with the second way. So let's just do it this way. So I always like to just set it equal to x. You can choose whatever variable you want to. I don't care. But I need to know, in order to convert this into its exponential form, I need to know what it's equal to. Well, I have no idea what it's equal to because that's the unknown. So I'm going to set it equal to x. So we're going to convert it to its exponential form. So I'm going to start there. So I'm going to start with the same base of 5, but then I'm going to switch these two. So I'm going to get 5 to the x equals 125 because these are switching. So 5 to the x is equal to 125. Notice that these just switched. They just switched. So now I have a base of 5 raised to the x power. My whole goal is to get this 125 as a base of 5. If you prime factor 125, so I get 25 times 5, and then 25 is 5 times 5. Isn't it made up of 3 5s? So I can replace 125 with 5 to the third. And then on the left side, I have 5 to the x. Well, logic reasoning would state that if I have the same bases, but their exponents look different, if these are equivalent statements, it stands to reason that x has to be the same as 3 for those statements to be equal. So I can ignore the bases and just set those equal to each other. X equals 3. In this case, there's nothing to solve. So if x equals 3, then that means that the log base 5 of 125 is also equal to 3. So you try B. Do the same thing. Your first job is going to be to actually set this equal to x. Then you're going to convert it to its exponential form, and then you're going to try to get the same base on both sides. So pause the video, you try it, and then check your answer. All right, so I'm going to set this equal to x, and then to convert it to exponential form, you get 4 to the x is equal to 32. I just switched these two around here. Then I want to get 32 as a base of 4. Well, unfortunately, I cannot convert 32 to a base of 4 because there's not an even number of 4s in 32. For instance, if I try to prime factor 32 and I factor a 4 out of it, 4 goes into 32 8 times. And then 8 just has a 4 and a 2. So I cannot convert 32 into a base of 4 because I don't have an even number of 4s in there. So you have to put on your thinking cap. What is 32 made up of? Oh, wait a minute. Is it made up of all 2s? Yes. And how many? 5 of them. 2 here, 2 here, and 1 more. So I could actually convert 32 into a base of 2 to the 5th. Well, that means that I can convert 4 into a base of 2 as well. And so I'm going to take this value 4 and change it to 2 squared. But that 2 squared is raised to the x. What do you do when you have a power to a power? You multiply the exponents. So what I really have is 2 to the 2x is equal to 2 to the 5th. Let's step back again. What did I do? I changed 4 into a base of 2, so 4 is equivalent to 2 squared. Well, this 4 was raised to the x, so the 2 squared has to be raised to the x. Power to a power, you multiply exponents, so 2 times x is 2x. And now I have the same base here as I have here. So since the bases are the same, I can drop them and just set their exponents equal to each other. So I can just set 2x equal to 5 and solve by dividing by 2. And so that means that x is going to equal 5 halves. So that means that log base 4 of 32 is equal to 5 halves, and we were able to do that without use of a calculator. So you've got it. This would be on the non-calc portion of your test. All right, so you've managed to get through that one, so don't let a fraction bother you. Remember, how can I get 32 out of that denominator and just let it be 32 to the what? So think about that, and then pause the video and see if you can get the 64 and the 32 into like denominators. So pause the video, really try to do it, and then restart it. Okay, so the first thing you should have done is set this equal to x. Then we're going to convert it into exponential form. So I'm going to take the base, which is 64, and I'm just going to switch these two. So 64 to the x is equal to 1 over 32. So before I try to get 32 out of the denominator, I'm going to just prime factor 32. I'm going to bring it all the way down to its prime. And so if you prime factor 32, you are going to get 5 2's. So 32 is the same as 2 to the 5th. And then 64, if you prime factor it, you get 2 to the 6th. Well, 64 is raised to the x. So remember, this is 64. I have to raise it to the x power. So again, power to a power, I'm going to multiply exponents. So I get 2 to the 6x equals, and then if I don't have like bases yet, but I'm very close to it, but my base is stuck in a fraction. I cannot have my base in a fraction down here. And so instead, I got to try to get this up here. Well, if you recall, if I move this in its opposite direction, the sign of this exponent changes, and it's going to change it to a negative. So as soon as I move this upstairs, the sign of that exponent changes to a -5. So I get 2 to the -5. And now I have like bases, so I can drop the bases and just set the exponents equal to each other, and it's a simple math equation from there. And so the value for x is -5 over 6. So that means that the value of log base 64 of 1/32 is equal to -5 over 6. All right, so I like those. Those are fun. You might not agree, but I really do like those. So let me make this small enough we can read. So let's do a word problem. It's kind of a simple word problem. I'm sorry it's going to probably look so small for you on your little Chromebook. Trust me, I can hardly read it without my glasses. Okay, so this is what they've done. They've given you a formula that you're to use, and this is actually much simpler than you think it would be. So it says the formula below, this formula right here, compares the intensity levels of an earthquake, where I is the intensity level determined by a seismograph, and M is the magnitude on a Richter scale. So that's your intensity, and that is your magnitude. And so in 1995, an earthquake in Mexico registered 8.0 on the Richter scale. So that 8.0 is considered a magnitude. In 2001, an earthquake of magnitude 6.8 shook Washington state. How many times more intense was the 1995 earthquake than the 2001 earthquake? So we're going to start with our formula and plug in the values that we've been given. So I was given this value here. So we're going to put that in as m sub 1. And then we were given this value here, and so we're going to put that in for m sub 2. So let's go ahead and write. So I've got log. Now notice that we don't have a base on our log here, so what's the base understood to be if you don't see it? 10, right? So this is a log base 10, and we have a quotient for our log that we're taking the value of. So log base 10 of I sub 1 over I sub 2 is equal to, and for m sub 1 we're going to put in 8.0, and we're going to subtract from that m sub 2, which is 6.8. So if I take 8.0 and subtract 6.8, I get log of I sub 1 over I sub 2, which is a ratio, is equal to 1.2. And so then our next thing that we need to do is get rid of this log. So to get rid of the log, we need to convert this to its exponential form. So remember, you got to know what the base is. So the base is right here. It's understood that this is a base 10, right? And so when I put it into exponential form, my base is going to be 10. And then all I'm going to do is switch these two things around. So I've got base 10 to the 1.2 is equal to I sub 1 over I sub 2. And then this I sub 1 over I sub 2 is actually going to tell us how many times more intense this was than this. So you don't actually have to find I sub 1 and I sub 2 individually. We just have to find its actual ratio value. So you're going to take your calculator and put in 10 to the 1.2, and you're going to approximate that. So I sub 1 over I sub 2 is going to be approximately equal to, and if you put that into your calculator and round, we'll round to 3 decimal places, you get 15.849. So therefore, the 1995 quake was about, because we estimated it, was about 16, because I'm going to round it up to an integer, 16 times stronger than the 2001 quake. All right, so we are going to start graphing logarithmic functions, and I want to start by comparing them to an exponential function. So here I have the exponential function y equals to the x. We have spent some time graphing that. And then this is the same base, so this is the log base 2 of x. We're going to graph this exponential function as well. But in order to graph this, I actually am going to have to use its exponential form. You will not be able to put into your graphing calculator a log of base 2. You can only put a log of base 10 into your graphing calculators and it'll graph that. It will not graph any other base other than 10. So you would have to graph it by hand. So I just want to point out something, that if I were to take this and put it into exponential form, I want you to see what I would have. So my base would be 2, right? But then these two are going to switch. So instead of x being my exponent, the y is going to become my exponent, and it's going to equal x. So 2 to the x is going to equal y, and I'm going to put my y on this other side. Oops, I didn't even switch them. My bad. This is what happens when I'm not paying attention to what I'm doing. Let's try that again. Let me switch it. So I'm going to switch it so that the y is here, but my x is here. I'm so used to having my y on the other side. So wouldn't you agree that this is the exponential form of this log function? And all I did was I kept the same base, but notice that I switched these around. So instead of y, here we have x. Instead of x, here we have y. We'll compare these two. Compare this one to this one. They look very similar, but they have the same base. But notice that the x's and the y's are switched on these two as well. Well, these are inverses of each other. If you remember the definition of an inverse, it means that the x and y's have been reversed. And so that's really how you're going to graph a log function, is you could, and you could actually graph this parent function and then just switch the x and y and then get your log function. But I typically will just graph this. So how are we going to do it? Let's start with this function first, this exponential function, and it should be a function of growth because 2 is bigger than 1. So these are the values we've chosen for x, y, because they're just typical values that we'll choose. And I'm going to plug those values in for x. So I'm going to plug all these values up here into the exponents. So 2 to the negative 2 is equal to 1/4. Remember, a negative exponent means that you're taking a reciprocal. And then 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. So let's go ahead and graph those. So I have -2, +1/4, and then -1, +1/2, and then 0, 1, that's our key point, and then 1, 2, and 2, 4. And if I connect those points, that exponential graph is going to look something like this. So that's something that we've been used to doing. And remember that this is your horizontal asymptote right here, y equals 0. And your key point is, and I'm going to actually write that key point. Your key point is 0, 1. So that's your key point. All right, well, let's graph this. Now, I'm going to use this right here to actually come up with my ordered pairs. So typically we would choose x, plug that in, and come up with our y. But notice that normally we would have to have y equals in order to choose for our x. And I don't have y equals, I have x equals. So in this case, it makes better sense to choose our y than it does our x. So I'm going to go ahead and kind of change what's on your notes here to do something a little bit different. This is going to be my x, and this is going to be my y. Well, I'm going to choose values for my y and find my x. So I'm going to choose the same values for my y here as we chose for our x here, because I'm going to plug them into this exponent. So I'm going to just choose these same values. So the values I'm going to choose for y are going to be -2, -1, 0, 1, and 2. And I'm just going to plug those values up here, and you're going to find that we're going to get the same values as we had over here. So let's go ahead and do that. If I take 2 and raise it to the -2, don't I indeed get 1/4? And if I take 2 and raise it to the -1, I get 1/2. 2 to the 0, I get 1. 2 to the 1, I get 2. And 2 to the 2, I get 4. So I'm going to plot those values. So I get to the right 1/2, but down 2. Or 1/4, sorry, to the right 1/4, down 2. To the right 1/2 and down 1. To the right 1, down 0. That's going to become your key point. And to the right 2, up 1. And to the right 4, up 2. So this is going to look like this. And what you're going to notice is that, remember how you're on the green graph here, your horizontal asymptote was here? Well, notice that this graph is approaching this line right here. Well, you ended up getting a vertical asymptote of x equals 0 here. So the asymptotes switch. Now remember, if your x and y switch, like they are here, this is the inverse of this because their x's and y's have switched. So it makes sense that if the x's and y's have switched, that if we had y equals 0, that our asymptote would switch to x equals 0. So I'm not drawing the asymptote in here because I've got two different graphs on here, but you would draw a dashed line here and label it x equals 0. And I have these both on the same graph for a reason. They are, and again, if you recall, inverses are reflections over the y equals x line. So I'm going to draw the y equals x line in here. And I think I'll use yellow. So this is the line of y equals x where every y is equal to x. And if you were to fold this graph on that line, this graph is going to lay exactly on top of this graph. And so, let me put in the key point for this one. The key point for this one is right here at 1, 0. So a couple of things. The key point switched from 0, 1 to 1, 0. That's an inverse. The x and y switched. The horizontal asymptote switched from y equals 0 to a vertical asymptote of x equals 0. And then these graphs look very, very similar. All right. Now, let's try to do one without, well, let me ask you this question. What if we were to graph y equals, let me choose a color that's different. What if I were to graph y equals log base 2 of x minus 3? What effect would that have on this graph here? We have one thing occurring here, so this is a translation. Wouldn't this whole graph here switch 3 units to the right? Remember, inside the function is always the opposite of what you think it is. So anything that can move right will move right, and that includes this vertical asymptote. So the vertical asymptote, which I'm going to go ahead and draw in now, is going to move right to here. And then every point on this blue line is going to move to the right 3. So I've got 1, 2, 3. So I have a point here, and then that's kind of in the middle. So 1, 2, 3, and then 1, 2, 3, 1, 2, 3, and 1, 2, 3. So you would end up with a graph that looks like this. So you can still use our knowledge of transformations, and you could graph a parent graph and translate it. Just move every point up, down, right, left, as many as you need to get your transformation. That only works if you don't have a shrink, a stretch, or a translation. If that's the case, then you need to actually do your XY table. All right, so what if we just have this? Describe how the graph of the function, and I don't think if we described that on the previous question. I think it asked for a couple other things. Let's make sure that we did everything on this question down here. So describe the, we didn't describe the domain and range, the y-intercept, or the asymptote. So let's go ahead and look at the blue line only, so we don't confuse everything. So we're just going to look at just this blue line. So your domain is from left to right. Well, we don't have any graph over here. And remember, your domain is your x value. If you recall, this x value has to be positive. That means it cannot be 0. And so our domain is going to end up being from 0 to positive infinity. And that's how come this asymptote right here occurs, is because it approaches, your x value is approaching 0, but it never can become 0. Your y value can be any number you want to, negative, 0, positive. So your y value spans the whole realm from negative infinity all the way to positive infinity. So that kind of answers the range question. So your range here is negative infinity to positive infinity. And actually, these are reversed from this green line. This green line had a domain of negative infinity to positive infinity, but its range started here because remember there was no graph down here for the green line, so your y never had a possibility of being negative, and so it went from 0 to positive infinity. All right, and then the other thing they want is the y-intercept. Well, the blue line doesn't have a y-intercept, so it has none. It has an x-intercept at 1, 0. All right, so let's go ahead and go on to example 5. Get that lined up. Describe how the graph of the function log base 2 of x plus 1. Notice this is not in parentheses. So this plus 1 is occurring outside of the function. So that means it's going to be moving up 1. So what you could do is you could graph the parent function of just y equals log base 2 of x. which we had done here, right? And then you could just move everything up 1. Or you could do it algebraically. So that's what I'm going to show you how to do here. Let's say that this was your first problem. You hadn't even bothered to do that parent function. I mean, you could still graph the parent function, move everything up 1, or you can use algebra. So let's approach it from an algebraic way. So they have kind of shown you right here, we've gone from here to here, but there's no explanation in here how we went from here to here. So let's talk about how do you take something like this and put it into its exponential form. So down below, I'm going to do the math for you. So we're going to start with, and I would prefer to, I like my log on the left. So I'm going to flip the equation around and write it log base 2 of x plus 1 is equal to y. And so my goal is, before I can put this into exponential form, I have to have the log by itself. I cannot change a log equation or a function into its exponential form if I have something being added or subtracted to the outside of that function. So my first goal is going to be to get this log by itself. So that means I have to subtract 1 from both sides. So I get a log base 2 of x equals y minus 1. Now I've got a base, and I'm taking a log of, and an answer over here. And so what I can do is take this base and switch these two things. And so that's what I'm going to do. I'm going to take my base of 2, and then I'm just going to switch the x and the y minus 1. So the y minus 1 becomes my exponent, equals x becomes my answer. And so this is the exponential form here of that log form. So this is what we're going to end up graphing. So notice that since this is what we're actually going to graph, and so I'm going to highlight that. So this is what I'm actually graphing. Then you have to decide, what do I choose? Do I choose my x or do I choose my y? Wouldn't it be easier to choose y so that you can subtract 1 from your y value and raise 2 to that exponent to get your x? I know we're used to choosing for x, but in this case, when we graph log functions, we're going to want to choose our y. And so that's why you see the y over here being chosen for you. Do you have to choose these values? No. No, I don't at all. But we can choose any number we want to for y, and I can tell you for a fact that x is going to be positive 100% of the time. Why? Because you have a positive base here being raised to some exponent. It doesn't matter whether that exponent is positive, negative, or 0. You're always going to get a positive answer here 100% of the time. So we've got these y values chosen. We're just going to plug them in here and get an x value. So here we go. I'm going to just write my general function 2, and then I'm going to do something minus 1 equals, and then 2 to something minus 1. I'm just going to prepare all of this for me to plug my y into. Okay, and so then I'm going to put my y in. So this is a -1 and a 0 and a 1 and a 2 and a 3. All right, and so I get 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 1, and 2 to the 2. So 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. So those are the ordered pairs that I'm going to plot. And so I am plotting positive 1/4, so the right 1/4 and down 1, to the right 1/2 and down 0, so that becomes my key point. I'm a little off there, sorry. To the right 1, up 1, to the right 2, up 2, to the right 4, up 3. And because I have a movement of up 1, my vertical asymptote of x equals 0 did not move. And I'm going to put a green line through this. And so that's what the graph of my log function is. And notice I did that without a calculator. And so now if you happened to compare this to the function above, you will notice that each of your ordered pairs has been moved up 1. All right, let's look at our last page. So for our last page, make it a smidge bigger. You might want to try this one on your own. It does have just one translation here, so I would highly suggest that you stop the video and go ahead and try this one on your own. So you should know about what's going to happen. There's going to be some movement to your asymptote as well. I would prefer that you try to show the algebra to get from here to here. So don't just take this, because you're not going to be given that. You have to figure that out on your own. So I want you to go from here to here and figure out the algebra down here. I'm going to show the algebra as well, and then you can compare your work and your answer and your graph to mine. All right, so pause the video, go for it. It's your last problem. All right, so I'm going to show the math here below. So I'm going to start with, again, I like to reverse that equation. I like my log on the left. Now it is important that the x plus 1 is in parentheses. So I'm going to start with my base of 2, and I'm going to switch the y and the x plus 1. Now from here I'm going to veer a little bit from what they have put here, because I don't agree with that. I don't want to graph something that looks like that, because if I'm choosing my values for y, then I want it to read x equals. So I do have to continue and go a little bit further, and I need to solve, whoops, I wanted a different color, solve this equation for x. So I am going to subtract 1 from both sides, and I'm going to get 2 to the y minus 1 is equal to x. So that's what I would put up here. So I would put 2 to the y, and then all of that minus 1 is what our x is going to equal. Because if we're choosing our y, because the y is in the exponent, and that's easier to raise the base up to that, then I might as well subtract 1 to see what my value of x is. So we've already chosen these values for y4. You do have to choose those values? No, you can choose whatever values you want to for y. Because y is in the exponent, it can be positive, negative, 0, whatever. So, but this just happens to be what we have here. So I'm going to go ahead and set up the work in the table. So I've got 2 to the something minus 1 equals, I'll put that exponent up there in a minute. So kind of working backwards in our table. And then my exponent is going to be my y. So my y in this case is negative 1, 0, 1, 2, and 3. And so 2 to the negative 1 is 1/2 minus 1. And I'm not going to put an equals there. 1/2 minus 1. So 1/2 minus 1 is negative 1/2. Whoops, negative 1/2. And then 2 to the 0 is 1 minus 1, which is 0. 2 to the first is 2 minus 1, which is 1, so it's cakewalk from here. 2 squared is 4 minus 1 is 3. And 2 to the third is 8 minus 1 is 7. So we're going to just plot, I'm going to move this over a little bit. We're going to plot our x and our y. And so, oh, and also, since we are moving, I don't think we wrote this, you should have anticipated that the graph is going to move to the left 1 unit. That's going to affect your domain and range, by the way. So our normal vertical asymptote was at x equals 0, so it's going to end up here at x equals -1. So let's go ahead and plot our points. So we have -1/2, -1, and then 0, 0. That becomes your key point. And then 1, 1, and 3, 2, and 7, 3. And so there's our graph. And so if you were asked what's the domain, notice that your domain always starts, there's nothing over here, so it always starts at this asymptote. So since the asymptote's at -1, your domain is going to start at -1 but not include -1 and go to positive infinity. Why doesn't it include -1? If you put -1 here, -1 plus 1 is 0, and this value has to be greater than 1. So it can be anything that's greater than -1, and so that's what this is saying, not equal to -1 but greater than -1. Your range covers negative, positives, and zeros, so your range is always going to be on these log functions negative infinity to positive infinity. Your key point is that 0, 0. Your key point is your x-intercept, and that's it. So good luck with your homework. Ask any questions.